Hello, I'm in a special government lab that's near Buxton, and I'm going to try and see if the scientists here can show me as many things as possible about noise, only using things that you might find at school or in your home. So let's go into this room here.
Hi Bob, how are you?
Very well, how are you?
Good. You're going to be telling me about noise today, yeah?
That's right.
Excellent.
That was Dr. Bob. So let's start by showing you how sound and vibration are very alike and that they both create energy. So the first thing you're going to need is a post-it note, some sesame seeds and a tuning fork, which you might be able to get from the music department in your school. Bob lightly touches the post-it note with the tuning fork and it causes the seeds to bounce up and down. Because the tuning fork is moving back and forward really quickly, it's hitting the underside of the paper really quickly. And that's what's pushing the seeds up and down. And that's how vibration can be transmitted as energy and also as sound. Okay, so let's go into the next room and speak to Emma because she's going to explain to us how things moving like a tuning fork can push the air and create sound.
Hi Emma. How are you?
Alright, how are you?
You going to tell me about noise?
I might do. Are you filming?
I might be.
For this, you're going to need a slinky and you're also going to need a friend.
So if you can hold on to those ends like that for me, hold lots of them together, that's it. And if you use two hands, that will really help. And hold it like that, brilliant. So if we imagine that each one of these rings of the slinky is a particle of air, when we release some energy through, what will happen is the energy is transferred along the slinky rather than a lump of sound energy being picked up and given to you. So if you can release one ring of the slinky bob and send it towards me, we'll see the energy travelling through.
Quite.
So if you can release another one, or have another go. That's it. I'm going to stretch it out a little bit more and have another go. That's it. And I'm going to do it from this end as well so you can see it.
Thank you.
There
Yeah,
we go.
yeah.
That was a good one, wasn't it?
That's
And because you've got a fixed end at that end as well, we're seeing a little bit of reflection coming back.
Yes.
So that's like a bit of an echo happening. Oh.
Great. Now, the next thing we need is an empty biscuit tin, and if you need to find one, then ask your teacher, as there's bound to be lots of empty biscuit tins in the staff room.
So sometimes sound can be annoying and we want to control it, and it can sound a bit tinny and ringy. So I've got a couple of biscuit tins here. And this biscuit tin is empty. Sadly it's got no biscuits in it. I'll show you. I think there's a few crumbs, but that's about it. No biscuits. Now if we sort of toss this tin around in the air a bit, you can hear it's a little bit ringy and tinny. Strange that, tin sounds tinny. However, if that was in a big factory or that's a machine in your home or something, that's going to be really, really annoying. But you can actually control that really, really easily. Here's another biscuit tin. Also hasn't got any biscuits in it. Actually, this is a chocolate tin. And it really doesn't have any chocolates in it, sadly. However, what it has got is a lid that's got some treatment, some noise treatment. And that's actually just gaffer tape, that silver, really silver sticky tape that you can use. It's just been put on the inside of the lid, and in this case around the outside of the tin. I can just show you the effect on the lid. So at the moment, if we take the noise control off, there you go.
Damping is used a lot in the manufacture of boiled sweets, and we can demonstrate this just by getting a hold of some marbles, 2 tin food trays, and then lining one of the trays either with an old bit of cloth or some rubber sheet. Now here's Bob to show you how it works. For the the next experiment, we're going to need the inside of a music box, a notepad and a coffee cup. But first, here's Emma to explain how this works.
So we're familiar with sound travelling through air because that's kind of how we hear things, but sound can travel through structures as well, and that can be a difficult concept to get your head around. So what I've got here is a little music box that makes a very, very tiny tune in terms of how loud it is. See if you can hear this. Now I'm going to keep turning the handle of this little music box, and as I do that, I'm going to put it down on the desk and we'll see if anything changes. And take it off the desk again. And so what you have there is the difference between airborne sound, which sounded really quiet, and going into structure-borne sound, which suddenly sounded like it was a lot louder, but it's just how the vibration and the sound energy is being transmitted through the structure. That's because there's a lot of space between air particles, so when you get the transfer of energy, like we saw down the slinky, then actually a lot of the energy is lost between each air particle. But in something solid like the desk, then the particles are much closer together and the transfer of energy is far more efficient. It effectively acts like a massive loudspeaker.
Now we're going to do the experiment with the music box, the mug and the notebook. And Bob's going to show you how isolation makes a big difference to the noise created by the music box, and that the cup only reduces noise significantly when the isolation is also. So, this is our last experiment, and for this you'll need a balloon, a metal nut and a coin. And what we're going to do is put the nut in the balloon, blow it up and then try and spin it round. Then we're going to take the nut out, put the coin in, blow up the balloon again and spin it round. And what you've got to do is guess which one you think would make the most noise.